welcome to this new video. In this video, we're gonna solve together this question you see in front of you. The question says, you're running a gas station business near a highway. Cars are passing by according to a Poisson process with lambda 54 per hour. So we have approximately 54 cars passing by per hour. The probability of a car stopping by the gas station is 1/9. So 1/9 of the 54 cars are actually stopping. And the amount of money they spend in the gas station is uniformly distributed between 200 and 550. So we have here two pieces of information. First, we have x, which is a Poisson distributed random variable with rate 54 divided by 9, which is 6. And we have y, which is uniformly distributed between 200 and 550. Now, what is the question? What does the question want from us? There are actually multiple parts for this question. So for the first part, we want to know what is the expected income during a 12 hours time period. So to know what is the expected income, we need lambda. We have lambda. We need t, which is here 12, and lambda is 6. And we need the expected value of y. So the expected value of y is 200 plus 550 divided by 2. And what is this? This equals to 375. So the expected income, let's say income in 12 hours equals to 6 times 12 times 375. Let's remember the formula for the expected value in the compound distribution. It's actually lambda t and the expected value of the other random variable. Here we have y. So this is exactly what we have here. So the solution here is, so this equals to 27,000 in terms of TL, Turkish lira. Okay, so this was the first part. Let's check the second part. So the second part of the question asks about the probability that the income is greater than 30,000 TL during a 24 hours time. So this is now 24 hours. So instead of writing it always, let's just say that Z is the income in 24 hours. So here t is equal to 24, and the expected value of z. Why am I finding the expected value? Because using the expected value and the variance, we can use the central limit theorem to find this probability using the normal distribution. So what is the expected value of z? Again, we can use this formula, and our lambda is still 6, Our t is now 24, and the expected value of y is, as we found it, 375. So basically this is double the number we found previously in the first part. Sorry, it's 54,000 TL. This is the expected value. Now we need to find the variance of Z. Now the formula is lambda t and the expected value of y squared. Now how can we find this? Let's take another color and let's come to this part here, and remember that in order to find the variance of y, what we used to do is expected value of y squared minus expected value of y squared, all of it. So now we want this. We can find this easily, and this is just this squared, sorry, not this. This is the 375 squared, and oops, this 0 is here again. So let's find this here. Expected value of y squared is equal to, now the variance, what is the formula for the variance of uniform distribution? It's b minus a, so basically 550 minus 200, right? 550 and 200, yes, divided by 12, and the numerator is squared. What does this equal to? This is equal to 10,208. Oops, this is not the expected of the y squared. This is the variance of y. And expected value of y squared, as we mentioned, it's just 375 times to the power of 2. So the expected value of y squared is equal to this number, 10,208 plus 375 squared, which is equal to 150,833. So let's bring this again to here to find the variance of z. It's going to be 6 times 24 times 150,833. What is this number? This is 200, or what is this number? 21,719,952. This is the variance. Let's just find the standard deviation. Of z. That's just the square root of that number, and it's 4,660. Let's just say take it like this. TL. here. So now we have Z is normally distributed with expected value of 54,000 and standard deviation of 4,660. Cool. Now here using Z will confuse us a bit, so let's just say I as in income. Okay, and here also I, and here I is normally distributed with mean 54,000 and standard deviation 4,660. So now basically the question we have here, probability that the income is greater than 30,000 TL. So what is the probability that I is greater than 30,000? And that's equal to 1 minus the probability that I is less than 30,000. Okay. So 1 minus probability Z is less than or equal to 30,000 minus the average 54,000 divided by the standard deviation 4,660. So let's do the calculation. So this is again 1 minus 5 of minus 5.2. So without looking at the Z table, we know that this is equal to 0. Because it's less than 4. It's less than minus 4. So this is directly 0. So the answer is 1, or 1 minus 0. And it's obvious because our average, our expected value is 54,000, and the question is what is the probability that this is greater than 30,000? So it's 1. So this was the second part. Let's check the third part. The third part of the question says what is the probability that the inter-arrival time between the 6th and the 7th arrivals is at least 15 minutes. So since our inter-arrivals are independent, it doesn't matter whether it's the 6th and 7th, the 8th and 9th, the first inter-arrival. So let's think about it as the first inter-arrival. Okay, so to solve this, we will take probability that first inter-arrival is at least 15 minutes, so greater than or equal to 15. And as we know, inter-arrivals are exponentially distributed. So if we take the CDF, it's 1 minus P first inter-arrival less than or equal to 15. And let's remember together the formula for the CDF for exponential It's 1 minus e to the power of minus lambda t. So that's, let's go down. That's 1 minus 1 minus e to the power of minus 6 times 0.25. And why is it 0.25? Because here we are talking about 15 minutes. And 15 minutes in terms of hour, it's 1 over 4, so 1/4. So first let's solve this area over here. That's 1 minus 1 plus this number, the e to the power of, what is this, minus 1.5. So 1 minus 1 will be 0. We have e to the power of minus 1.5, and this equals 0.223. So 22.3% probability that the interrivals are greater than 15. So now let's check the fourth part of the question. The fourth part of this question asks that, given that 8 minutes passed after the third arrival, what is the expected time between the third and fourth arrivals? So here again, we ignore the specification of the number of arrival, third, fourth, seventh, eighth. The information needed here is that already 8 minutes has passed. So 8 minutes have passed. Okay, this is a key information. But however, interarrival times, as mentioned before, are exponentially distributed, and exponential distribution has the memory lessness property. For this reason, we just take the normal expected value. So normal expected value is equal so of interrivals is equal to 1 over lambda, which is 1 over 6. In terms of hour, 1 over 6 is equal to 10 minutes. Now, this is not the answer. This is the normal expected value for interarrivals. But here we know that already 8 minutes have passed. Therefore, for this situation, just for this question, the expected time between the third and fourth arrival, so let's say fourth interarrival is equal to the 10 minutes that is normally calculated plus the 8 minutes that already have passed, which is equal to 18 minutes. And now with the fifth part of this question, it asks that there is a car wash in the facility, and cars pass stop by the car wash with a Poisson process uh, having lambda 8, so with the rate 8 cars in an hour. Note that cars come for either gas purchase or washing. They can't come for both. What is the expected number of cars arriving at the whole facility during a 30 minutes time period? So let's remember we had a gas station and lambda was 6. And now we have car wash. Let's call lambda G and lambda C. This is 8. So we have a merged process right now. And for the merged process, the lambda total is equal to lambda G plus lambda C, which is equal to 14. So now we have 14 cars arriving per hour. But now we want what is the expected number of cars arriving at the whole facility during a 30 minutes time period. So it's basically, let's call it expected value of cars arriving at the facility. That's 14 over 2, so that's 7. And now let's check the sixth part. Next, this part of the question asks, what is the probability that the first customer of the car wash arrives before the first customer of the gas station? And this is an easy question. It's basically when we have a merged process, then we will have something like this, for example, plus this will give us the probability if gas station customer before car wash. And what we want is this, car wash before gas station, car wash customer before gas station. So we said the car wash, the lambda there is 8, and the summation of both of them is 14. So the solution is going to be 8 divided by 14, that's 0.57. Now for the 7th and 8th questions, uh, they are similar to each other. So the 7th asks, given that one car arrived during the first 3 minutes, what is the probability that the car arrived between first and second minute? And 8th question is exactly the same question, but adding an information that lambda is 30 here. So to solve these questions, we will solve them similarly. Let's assume we have time intervals. Here we have 0, 1, 2, and 3. We know that a car arrived here during this interval. So it can arrive here, it can arrive here, and it can arrive here. This question, lambda here, lambda equal to 30, does not affect this question. So 7th and 8th parts have the same answer. So if we know that a car arrived in the first 3 minutes, does it come, did it arrive here or here or here? The answer is just 1 over 3 because it can arrive at any one of these time intervals. So Basically, the answer for both these questions is 1 over 3. By this, we solved all the parts for this question. Um, you can find this document attached as a PDF with the video. I wish you good luck and see you in the next videos.